Excellent. Yeah, so go ahead, Sarah.
All right, awesome. Good morning, everyone, and good, I guess, whatever time you are, everyone on the planet watching this. So I'm here to present analysis of molecular spectra using SOFIA EXES. And just a brief overview. So I designed this talk to let you know everything that I wish I knew when I was starting out working with EXES data. As an example, to guide you through the analysis process, I'm going to talk about hot cores and their importance, and then use as an example our observational survey we had towards one particular region, Orion IRC2. And then I'll go over the basic analysis methods, so getting you started with plotting your EXES data, how do you normalize it, find the molecules, fitting it to Gaussians, drawing rotation diagrams, and then also on simulating spectra. And I'll wrap up with some applications and a brief note on more complex situations you may find yourself in. Oh, first, hot molecular cores. So these are some objects in astronomy that require introduction. Stars and galaxies don't require introduction. So hot molecular cores are a very specific stage in star formation. And so their normal definition is that they're warm and small and dense, and they're associated with high mass protostars. And on the bottom plot here, you can see that we begin with the cold, clumpy molecular cloud. It starts to condense, and then the protostar begins to heat up the surrounding gas. And what this does is it releases a lot of molecules that had previously been ice formed on the dust grains in the molecular clouds, and now they're being heated up and released. But this is before later stages when everything gets ionized. And so this stage, the hot molecular core stage, is a very interesting part of the star formation process for looking at molecules and finding a lot of complex molecules. And typically, a hot core will surround a protostar, but this is not always the case. There's sometimes some other situations which I'll cover later. And so there's some wide-reaching implications of the study of hot cores. And so these massive protostars act as flashlights that are probing the state of the interstellar medium in the very early stage of star formation. And these types of regions that have massive protostars, our own sun may have formed in such a region, even though our sun itself is not massive, but other stars around it may have been massive. And there's studies showing that perhaps the chemistry of our own solar system was inherited from a hot core region. And then we can find the molecules in this gas that are the precursors to probiotics that will eventually give rise to life on places such as Earth, perhaps. And so by studying hot cores, we really get to study the origins of these molecules. And so far within the Milky Way, dozens have been discovered. And very recently, a handful have been discovered in the LMC. And actually just, I think about a month ago, some were discovered in the SMC. So that's very exciting to get to see also hot cores in other galaxies. And here I just list a number of overview papers if you're interested to read more up on the background of hot cores. And we can see here MONR2, AFGL 2591, NGC 7538. These are all images of hot cores or their surroundings. The AFGL image, you can see a jet forming from the individual star. Whereas MONR2 and NGC, these images are more showing the surrounding cloud region that formed the star, and then the star is eventually going to ionize. On the bottom is just a cutout of one of the hot cores discovered in the LMC with an artist impression. And on the left is an illustration of AFGL 2591. And so you can see the protostar being surrounded by a dusty disk of gas that has lots of molecules in it. And so for the mid-infrared specifically, it has a lot to offer. So most surveys tend to be in a radio or sub-millimeter to far infrared because these wavelengths tend to be more accessible from the ground. So that's where you find most of the observations. But when you're only looking at the longer wavelengths, you're missing out on a lot. And so the longer wavelengths tend to probe the colder outer regions of the hot cores of these regions, whereas with the mid-infrared, you can see the hotter inner regions. And another aspect is that there's some molecules that you can only see in the mid-infrared. Those that don't have a permanent dipole moment, such as methane, and then also rho vibrational transitions are unique to the mid-infrared. However, one other issue with looking at the mid-infrared is, of course, there's a lot of atmosphere here. So you can go to space. However, the space missions have lower resolution, including the PAST, ISO, and Spitzer. And also JWST does not have such high resolution that you can see individual molecular transitions. But with EXES, you can. And so now we're going to get to a bit of an atypical case, the Orion hot core. So this was actually the first hot core ever discovered. But despite this, it's a bit different. So it's situated in the Orion BNKL region. And this is it's the closest massive star forming region to us. And so this means it's also the best studied massive star forming region because it's so close and it's really accessible. And about 500 years ago, there was an explosion. It pushed BN and Source I apart. These are two massive protostars. And in pushing them apart, it created this explosion. You can see on the bottom image, there's these famous fingers of H2 emanating from the region as a result of the explosion that happened. And so this led to a lot of complex and strange geography in the region. And so the Orion hot core itself is very dense, full of a lot of molecules. It's warm, so it follows all the definitions. It's in this high mass star forming region. But studies of the Orion hot core have found that it itself is externally heated, and there doesn't seem to be an embedded protostar within it. And what the interest of our survey is, we're looking at IRC2, which is the second brightest mid-infrared source in the region. The brightest one is BN, but this doesn't have a lot of molecules towards it. And so Orion IRC2 probes the very edge of the hot core. And this is where we're pointing EXES towards. IRC2 itself is also a bit mysterious. It's possibly scattered radiation from radio source I or source N, or may also be a cavity. So it's not a star itself, but it is a mysterious bright object. And in the left-hand image here, so we have the EXES beam in green, it's centered on IRC2. The colored contours here in the background are the mid-infrared flux of the region taken with the Subaru telescope. And just to also compare the beam sizes, EXES has a very smaller beam compared to ISO, the dotted brown beam, which was huge. And so the ISO beam, it's difficult to isolate individual objects with the beam, whereas EXES, we can really zero in on IRC2 and see exactly what's happening towards this source. And so the survey we conducted with EXES ran from about 7 to 28 microns. And just showing you briefly on the right, there's an ISO survey with that was also towards Orion IRC2. And you can see it's only able to resolve the strongest molecular features. While zooming in on the bottom, the green flux is from EXES itself. So here we can see with EXES individual lines that we can study in great detail. And these lines would be indistinguishable from the continuum. And so JWST, which has similar resolution to ISO, will also not be able to see in as great detail as EXES did. And so showing just overall the range of EXES and the atmospheric transmission. And so there's about 2 windows that are difficult to observe, both with EXES and from the ground, around 10 and 15 microns. Before the rest of it, EXES compares much better to the ground, so EXES can access the rest of its range. On the left, there is a lot of atmosphere, but there's enough windows in there that EXES can also observe around 5, 6, 7 microns. And of course, between 10 and 15 microns, there's a window where Mauna Kea is comparable to EXES. And there you would usually use ground-based instruments because not much is gained by using EXES. So now let's begin to import our EXES data. And so you're generally going to encounter 2 different types of files, either merged order files, where all the different orders are merged, or you're going to look at orders that are stored in separate arrays. So these are the CMB or SBC files. I'm just using Python code as an example, but of course you can easily write code in whatever language you want. And so in these files, you'll get the wave number. EXES is stored in wave numbers. And then also an unnormalized flux. And you'll also get an ATRAM model that's not tuned to your specific observation. So this is a atmospheric model. And then you're also going to get the variance, which as an end user, you're probably not going to require at all. So you don't really need that one. So now we've loaded our EXES data and we plot it. And of course, the first obvious thing is that our flux is not normalized. And also it's, our flux is not normalized and it's also above the atmosphere. Whereas the atmosphere model is normalized. So we have to fix this. And there's several different ways to normalize the data. There's a quick method, which I'll go over in the next slide. And then the next 2 methods are if you have a calibrator. This is like an object taken with your observation, typically one without any spectral, without molecular features, featureless star like Cirrus. Then you could divide by that, but those are not commonly taken with EXES, so usually you're out of luck. And then you could also divide by an atmospheric model, an ATRAM model, or one generated using NASA Planetary Spectrum Generator. And I encourage you to check out Curtis's talk from last year where he covers these, how to use these in detail. And then he also has a really good introduction into what EXES is and the available data products and the earlier data products that I'm not covering. And then the fourth thing is that in some situations you may have an uneven baseline. And so then you need to divide by a polynomial. So I'll also get to that afterwards. And so if you want to just quickly normalize, just to have a nice look at your data, you can identify some regions where the flux is flat and where the HML is close to 1, and then just take the mean flux of these regions, divide your entire flux by this, and it will be roughly normalized. And so this is good for a quick look when you don't want to invest too much time analyzing. And then it lines up the telluric features, and then it's really obvious which line is a molecular line. Well, this one's huge, so it was obvious before. But if you have smaller lines, this will make them also obvious. But as you notice, the model and the flux don't quite fit anywhere. So we're going to need a better model, because later for these types of lines, you notice there's a bit of an atmospheric line over our molecular line. And we're going to want to divide out the atmospheric model. But the model that comes in the EXES file is not tuned to our data. So we're going to need a better procedure. And so another method you can do is normalization by tuned HRAM model. Curtis also covers this in his talk, but I'll reiterate a bit here. And so you look at the FITS header file from your of your data you're interested in, and you can grab the altitude, latitude, and zenith from that. You go to the HRAN website given here, and you can enter in this information, the wavelengths you're interested in. You also want to choose R equals 0. That's the resolution for no smoothing. And then you download your HRAN model as a text list. And then what you can do with this is you will smooth the HRAN model yourself. If you're using Python, there's SciP Gaussian filter 1D, so that the HRAN model's resolution will match the resolution of your particular observation. And then you also want to find a normalization parameter for your flux that will also normalize it to match the HRAN model. And so to do this, you want to find the normalization parameter and you want to find a smoothing parameter. And one of the good functions to use this is the SciP minimize function that will find the minimum difference between normalized flux and smooth HRAN model. So you can see the result here is much better for matching the atmosphere. It's not perfect, particularly if you notice on the right for the large line. And so typically for the larger atmospheric lines, the model doesn't really match up perfectly. However, if your molecule of interest is in one of these giant lines, a lot of it is lost anyways, so you're probably not going to be able to analyze it anyways, so it matters less. It's more for the smaller atmospheric lines you want to make sure they match up so that you're able to properly divide out the atmosphere for molecules which overlap with it. And so the next case is uneven baseline. And so this is essentially if this happens usually around the settings that are around 300 to 400 wave numbers. And no one's quite sure why this happens, but it is a feature of EXES that you need to correct for if you have molecules where the flux is wavy. And so this is simply taking the baseline and fitting it to a polynomial and then dividing out that polynomial. If also your flux, if there's also some atmosphere in the region, you also then want to divide out the atmosphere. And so this essentially just straightens out the flux. You can find a polynomial either by just eyeballing, guessing which polynomial fits best, or you can write an algorithm for that. It's really up to you. Okay, so now we've normalized our EXES flux, everything looks good, but we need to know what molecules we're looking at in order to take our analysis further. And so one of the ways to get familiar with what kind of molecule it might be would be searching the literature. So ISO is a good resource. So see if someone looked at your object with ISO and see if there's any molecules taken with ISO in the region you're interested in. So in our case, around IRC2, around 13 micron, we see that they found acetylene and HCN around there. So those are good candidates. If there's not ISO paper towards your specific object, you can look at other objects and see what was found within their wavelengths. And so I just pasted the names of 3 papers here that have pretty extensive mid-infrared surveys for hot cores. That could give you lots of molecule ideas. And so in order to get the transitions of these molecules, you need to go to some databases. So the first one I always go to is Hytran, because this is the most user-friendly. They even have their own Python package that you can integrate into your own code. And it's designed for molecules that are in the Earth's atmosphere. It's for atmospheric science. However, these transitions and the quantum parameters are the same everywhere, so it doesn't matter if it's just for Earth. It's going to apply to space as well. There's another database, Geisha, which has a lot of overlap with Hytran, but there are a few molecules it has that Hytran doesn't, notably HNC. And then if it's not in those databases, you can try the EXEMOL database. So this database is for the purposes of studying exoplanet atmospheres. But it's a bit less standardized than the first two, so it's a bit trickier to use. So you want to check out Hytran and Geisha first. And another way, if you don't want to check the literature and you don't want to know what your molecule is, I've also plotted here. It's probably a bit hard to see on the computer screen, but I'll put my slides online so you can zoom in later to see which molecules are where. So I've just taken, I think it's maybe around 10 most common molecules and plotted them here, plotted all their transitions. So then say if your observation's around 20 microns, you probably want to see, maybe it's SO2. You go 22 microns, maybe it's CO. This is the first thing I want to check out. So now let's identify our line. So from ISO observations, we could guess maybe it's acetylene, maybe it's HCN. So we download these molecules from the database. And then we also want to shift the transition by the LSR velocity of our object. So if there have been previous high resolution publications for near infrared or mid infrared, you could grab velocities from those and they'll probably match up the molecules you're seeing. So in our case, we had a previous EXES publication, so we could guess, it's around -7 kilometers per second. If there is no publication in mid-infrared or near-infrared, then you might want to look at longer wavelengths to see what LSRs they found. But in my experience, these don't always match up with what you see at our wavelengths. So if you can't find anything, then you're just going to have to guess and see if molecules are consistently shifted by a certain species line list. So in our case, we plot some acetylene, but nothing's really matching up. However, when we plot HCN, we find it matches up perfectly with a very strong transition. And so this molecule is probably HCN. Of course, here we're only looking at one transition, and so what you want to do is look at the entire setting and make sure it makes sense so that every strong molecule of HCN matches up with the line. And that's how you kind of carefully unpiece the picture of what molecules you're looking at. So in our own survey, We identified over 300 features and identified quite a few molecules. Most of them were in absorption, a few were in emission, and then we also could find 2 isotopes. So when you're looking for molecules, you want to just find the most common isotopes first. And if you have some mystery lines left, you want to search, okay, the next most common isotope. See if you get those. Because then there's a lot of interesting chemistry that can be done if you catch more than one isotope of the same molecule. And then also, if you notice, some of our lines are a bit asymmetric. For example, you can see in the methane line. And so this means there's at least 2 velocity components that we can see here. So now that we know what molecules we have, we want to fit them to Gaussians. And so I found when fitting with Gaussians, it's very important to select your baseline. Here I'm only showing very tame, nicely behaved examples, but sometimes the baseline around your molecule might be funky. And so you want to play around a bit and choose how much left or right of the molecule you want to give to the fitter so that it will fit the line properly. And so we use formula from Indriolo 2015 to fit our flux to. And then once you fit and you get the quantities, you can get out tau, the optical depth. You can then find the column density of the individual transition. And of course, if you see there's more than one component, then you might want to fit to more than one Gaussian. So here are some of our lines. We fit to double Gaussians because we're seeing more than one velocity component here. And another thing that you want to do is, of course, if your line overlaps with some atmosphere, you want to divide out using the tuned HRAM model or the PSG model, whichever one you're using. Once we have our Gaussians, then we have a list of column densities for all molecules. And then we can get from our databases the energy, statistical weights, and we can fit we can use the Boltzmann equation. This is found in Goldsmith and Langer, 1999. So here on the plot is HNC. So you plot the transition energies for each transition, and then versus the natural logarithm of the column density over the lower transition statistical weight. And you see that it follows a linear line, and so from this line we can get the temperature and the column density, overall column density of this species. And then also we find the LSR velocity just by averaging the LSR of each transition. And then a note on emission lines. So analyzing molecular emission lines, it follows a very similar procedure. The equations for the Gaussians are slightly different, but in the end of the day, you're fitting to a Gaussian, and then you're also using rotation diagram. However, the complexity with emission lines is that you need to convert it to an absolute flux and not a normalized flux in units of Janskis. If EXES observed a calibrator on the same night, that's great. You can use that because something like, say, they observe Vega on the same night. It's a well-known star, and you know it's absolute flux. So you use that to compare to your data. You might also want to look at ISO data on Ursa. That also has the absolute flux. But you have to be careful because it depends on the region your object is in versus the beam size. So if, for example, in our region, Orion IRC2, it's very complicated. And there's other objects, so we can't really trust that all the flux in the ISO beam is coming from our object. And then if that fails, you might have to go back to literature to see if other instruments in the mid-infrared observed it. and give a flux for your object at the wavelengths of interest. So that aspect is going to be very dependent on your observations. And our next situation is, what if we have so many lines, it would take you forever to fit them all to individual Gaussians. So this is what happens with SO2. It's a very crowded molecule. The lines tend to be super dense, all running all together. Hundreds of transitions we see. And so for this, you want to be lazy and fit everything at once. And so you can work backwards from the Boltzmann equation, treating column density, temperature, velocity, and the width as inputs. And then these will generate simulated spectra. But you want the simulated spectra that fits, that best fits the flux that you observe. And so for this, you want to use an optimization function. And a very commonly used package is MC in Python. It's very popular. It might be the most popular. I haven't done a survey, but a lot of people use it. And so you can use this to find the parameters that best match your flux. And so this is just the result showing in green offset. So you can see it is a model of the SO2 that was generated that then I ran through MC, and it found, okay, what parameters fit it best. So from there, we can get out the temperature and column densities we're interested in. And so this is all great. We measured our molecules, but what does it all mean? And how do we circle this back to astronomy? And so through this chemistry, we can actually use these very small picture to bring it back to the big picture of our regions. So essentially, these very tiny molecules have big implications into these huge astrophysical regions. And so the first example I'm showing is from our own survey. And so the Orion BNKL region has several classic components. There's the hot core, that's the hot dense region full of molecules. And then there's also extended ridge. So this is just the ambient gas of the region. And then there's the plateau. So this is an outflow from radio source I. It has two flows, low velocity flow, high velocity flow. This is a shocked gas with a very wide widths. And then much wider than the other components. And then we have a compact ridge, and this is where the plateau is hitting the ambient gas of the extended ridge. And these components were identified in the 80s and have been very well studied by longer wavelength surveys. And also their velocities, LSR velocities, their widths, their temperatures, very well known, very well studied and established. However, by looking in mid-infrared, we found that our components have different velocities and widths and temperatures from these four components. And so we were able to look in the mid-infrared and find two completely new kinematic components that everyone missed because no one's there haven't been any large surveys in the mid-infrared before. And so our initial motivation for a survey is looking towards the hot core, probing the edge of it. But what we found was we have a bit different velocities from the hot cores. And so we're able to identify these two clumps of gas that are not perhaps associated with hot core itself, but still have the same molecular richness and abundance of a hot core, and so still exhibit its chemistry. But we still need to do more work to figure out what they are exactly. And so for the mid-infrared, you're able to find distinct properties from other surveys. And so we're able to add another piece to this really complicated, really well-studied region that we wouldn't be able to without EXES. And then also with JWST, this region's too bright, so we won't even be able to see this with JWST. And the second example I'm giving is work from BAERI et al. 2020. And so this is towards two of the classic hot cores, AFGL 2136 and 2591. So here again in the right is an illustration showing that these are hot cores that are a protostar, and we're probing the gas that's around the protostars, and you can also see jets coming out in the image. And so for their paper, so they looked from 4 to 13 micron, and then they also combined data from EXES and TEXES. TEXES is like EXES, but it's on the ground in Mauna Kea. So it looks at the regions where the atmosphere is comparable to EXES. And then also they used iShell and Mauna Kea. And this is in the near infrared at shorter wavelengths than EXES. And so the near infrared also probes similar gas and components to mid-infrared. And so they found absorption lines of several species, and also because it's a traditional hot cores, the temperatures were much higher than those in the Orion hot core. And so by studying these molecules, they're able to infer that the absorption lines are tracing a disk around the protostar. This is shown in the left-hand image. And you can see how each wavelength band probes a different layer in the onion of the protostar. And then they could calculate the vertical temperature profile of the disk around the star from these molecules and figure out what kind of heating mechanisms are used and what kind of transport is used for moving these molecules around the disk. And so this part very close to protostar is traced by near and mid-infrared, whereas other observations in the submillimeter and longer are probing an outer envelope. So you can't even see this region with the other observatories. And so just these two cases really emphasize the importance of the mid-infrared and what you can only see here. And so I'm just going to quickly glaze over some more complicated situations you may encounter. So one of them is optically thick lines. So these are lines with flat bottoms or a lot of scatter in the rotation diagram. And there's two solutions to these. One you can find in BAERI 2020 using a stellar atmosphere model for abundances. And also in BAERI 2022, they use curve of growth analysis to get around this. If you find that your molecules are non-local thermodynamic equilibrium, so this would be if your rotation diagram's not straight, then you would need to use non-LT modeling for it. One example is RADX, that's really commonly used. However, you need collision coefficients for this. And I wrote here that I'm unaware of a database with collision coefficients that covers mid-infrared. But I noticed in David's talk, he mentioned a database. Can't remember what it's called, but I haven't looked it up. So maybe that one covers mid-infrared. I have to verify that actually. But it's going to be a bit of a hunt for your collision coefficients if you're in mid-infrared. And just to finish up, so I developed all these tools as a Python toolkit that does a lot of things and makes it really easy to analyze EXES data quickly. I intend on making it publicly available at some point in the future with documentation, but haven't yet now. But if you're interested, just contact me and I'm happy to collaborate. And so I leave enough time for some questions, and I thank you for your attention.
Thank you, Sarah. Very interesting talk. I don't see any questions in chat at the moment. Yeah, but please type your questions in the chat or raise your hand. Maybe in the meantime, I can use my prerogative as the chair of the session. So when you're showing your baseline fitting, maybe I missed it, but I presume that you identify spectral windows that you exclude from the fit. And
You mean this one?
yeah, your baseline polynomial fit. And I was wondering, because it was not indicated, I presume you use Python for this?
Yes, I'm using Python. So actually, to dig into this a bit more, I wrote a peak finder that automatically identifies peaks, and then you would exclude the peaks, and you would have only left the bits that are baseline, and fit that to the polynomial. It works in nice regions like this, the peak finding automated method. If it's a complicated region, then you just have to identify by eye what the baseline is.
Okay, very interesting. Yeah. I presume it's going to be part of your public release as well if when it comes out.
It's in there. Yeah.
Excellent. Thank you. I see the hand of Beachy.
So that was very nice, Sarah. When we were doing the fuse analysis, which had, for instance, for molecular hydrogen, it had a lot of faint lines combined with a lot of high opacity saturated lines. Steve McCandless and his group used a method where he was fitting in opacity space. Have you considered trying, because that sort of semi-automatically takes care of saturation even when you don't see it. Have you considered doing it in that way?
No, I actually hadn't come across that method in the literature. What was the object they were looking towards?
Oh, I have to go and dig out the exact objects, but a lot of the fuse data were analyzed in that way. So in the far ultraviolet. But we can talk offline, but
Yeah.
it is a very nice trick because it sort of automatically accounts for saturation.
Yeah, I would actually be really interested in reading that paper and learning about that.
Let me get back to you.
Yeah, thank you.